Hello everybody, welcome to my devlog. This is a new series I'm working on documenting the work I've been doing on my new game, Artifice, a game about fantasy engineering. In this game, you play as an artificer. Item creation takes the form of puzzles. You'll need to balance the interactions of elements, the power being delivered to runes, and the current going through the conduits. Like wires, conduits have ampacity. If you exceed it for too long, the wires will blow. This will create a short to ground, making it more likely other conduits will blow in turn. Crystals power the devices, and it also has ampacity. If it blows, it's game over. Usually a catastrophic explosion. This is the game running over here, you can see. So, my main inspiration for the game, there's a couple. One of them was the anime Dahlia and Bloom. I really like that, and it kind of inspired me in part to make a game about artificers. Another is a YouTuber here by the name of Real Civil Engineer. He plays a lot of really simple indie games, and I think probably it's just seeing a lot of simple indie games kind of made me think, I could do that. So that's part of the inspiration there. You can see this is just a little circuit I made for the heck of it because it makes a nice little blinking red and blue light. You can see the water charges, they can move just fine on a fire conduit, but if you tried doing it the other way around, if you tried sending fire through a wire conduit, the resistance would be ridiculous and it would just it wouldn't move very quickly. But these move fine like this. You gotta generally consider the how the elements will interact with each other. There's actually a chart. Let's see if I can bring that up very quick. Let me pause while I go look for that. This shows you generally how the elements interact with each other. This is fire, wood, water, metal, earth. So, fire creates earth, earth creates metal, metal creates water, water creates wood, wood creates fire. Fire destroys metal, metal destroys wood, wood destroys earth, earth destroys water, water destroys fire. So, in this case here, you can see that since fire doesn't destroy water, water can move through a fire conduit just fine. But because water destroys fire, fire cannot move through a water conduit. Try going this way, you're going to have problems. You're generally fine as long as you're going in the direction of the arrows. I think it does, they do more damage to the conduits themselves. Like, these would be degrading the conduits, likely, but that's some other time. I don't think it's currently set up to do that. But yeah, okay, so other than blinking lights, what might you want to do with this? Now, most of this here is actually the sandbox area. Most of them take the form of a puzzle level where there's a clear objective as to what you're supposed to do. But this one, this is basically where I just build random crap. So let's consider instead of that, we'll go ahead and we'll put it up there. Let's bring in, this is the inventory area. There's a lot of different things in the inventory. It's basically just everything that exists right now is in the inventory. These are the nice little guys. Oh, no, actually I already have transistor runes in there. They're right there. Alright, transistor runes are the ones we were looking for. So, we're going to go ahead. Let's plop a couple of these guys. These are switch runes. And we'll plop a couple of these guys. And let's go ahead and put that guy there. Some of the engineers out there might already know what this is going to be. But, oh, let's stop that. I don't want it doing that right now. So, let's see. We will need this to go down here. So, transistor runes, they wire up in a specific sort of way. First you connect the power, then you connect the base. So you go collector, emitter, then base. Base needs to come off here, so we go there for the collector, emitter, and then we can go here to here. And we'll do the same over here. Yeah, I didn't need to do that, but that shouldn't break anything. And then that will go through that switch and into that base. Now, the setting of the electrical engineers out there probably recognize an OR switch when they see one. You can see here, no power is going to there. Turn that on. That power. Now, if you're wondering why the numbers disappeared, it's because they're moving too fast to see, basically. The speed in which the numbers will move is going to be based on their current. So that's just going to be your V over R. So if they go too fast, essentially I kind of had to do that because if they're moving slowly, then they're not going to be delivering their charges fast enough to do what's needed for things that actually where it matters. So yeah, turn this one on, turn that one on. That one's still kind of flickering here. That's interesting. Yeah, that's an OR switch. And an OR gate. And you can also make instead of an OR gate, let's see. I want to delete these for now. Power should go here. This should be an AND gate, which will be this and that. Again, power just runs straight through. This one goes in there. This one into there. And you can see how it goes. It's like when you wire the order matters so that when you wire it in, it goes. It could be on this side, it could be on this side. You don't have to like rotate and fiddle with it like that. But yeah, you can see here, only when both of them are on do you get an AND gate. Or does you get power, because that's how an AND gate works. You can see that power value is incorrect. I need to do something about that. I'm thinking of taking the power off of this one, but it'll give you some indication. That max current's also wrong. The max current for these is actually 5 amps, not 1,000. But you can get some sense of how the current's actually flowing through these things. And yeah, these are salamander blood. That's this particular type of conduit is called. There's a number of different types of conduits. They give different resistances. Let me actually bring some of them up here. That's this one, the salamander blood. You can see the conductivity is 200. Sounds nice. It's really not. Compared to wyvern blood, where it is, yeah. What is that? 1.4 million, I think it's sieverts per inch. Again, engineers will understand. That's your that's the conductivity of copper wire, basically. So there's three basic levels. We have a poor conductor, like salamander blood, a good conductor, like this, which is basically this conductivity of copper, and you have superconductors, where the conductivity is infinite. Substrates are another thing. All these say wood substrate. They shouldn't. They're actually different substrates. I think, yeah, there's 5 of them because there are 5 substrates: wood, water, earth, metal, fire. They basically help prevent magical buildup, which is this game's version of what would it be? Heating that happens in a wire. You know, when a wire heats up, the joule heating, I think it's called. Essentially, if you have, what happens is when a charge moves through a wire, it causes a buildup of the opposite charge. So what you want is a substrate that will destroy the charge that builds up. and that prevents it from overheating on you and frying the wire, basically. Yeah, copper has an accurate conductivity. Anyhow, yeah, and there's different types of crystals as well. These also have both a rarity and a quality. The garnet here is the lowest quality. It's got little information if you want to pause and read it. But yeah, it's got 9 volts. Its mana flux is 1 to 5 mu. It's just what I call many units. Essentially, what it means is that 1 to 5 is what you see when this is flowing. What is this doing? Why are you not moving? Anyhow, when it is flowing, you'll notice that these numbers, they vary between 1 and 5. Now, the ones aren't as common. Largely, I at first used just a random number generator, but I changed it up to use Perlin noise instead. So actually, 3 to 5 seems to be the more frequent. Oh, that's why it's not moving, because it's paused. Sure. Oh well. Yeah. Make it long enough, you can see. So you rarely see 1s. They don't come up all that often. It ends up being mostly 3, 4s, and 5s. Sometimes a 2 might show up. I'd like it to have a little bit more range, but yeah, there's a 2. But I'm fine with the way it is right now, actually. Anyhow, yeah, that's what the mana flux means. Again, the max current is incorrect. These also have a max current of 5 amps. Oh, but speaking of max current, we got fuses over here. 5 amps. Now these ones, they're made to blow a lot faster. Essentially, if you exceed the 5 amps, they will blow. And that's good because it means that your wires, your crystals, whatever, they're not going to blow. Unless you've managed to send so much current through that the wires blew ahead of the amp. Essentially, it'll work backwards from the source. This isn't exactly accurate, but it's more fun that way, so I'm fine. Capacitors, we have similar. The capacitors, they don't quite work like real-world capacitors. Real-world capacitors, like the voltage, it drops as they discharge, and it increases as they charge. And I think your current goes down as it's charging, but as it's discharging. But the problem is because, as I mentioned, the speed of the charges is based on the voltage over the resistance. If the voltage is constantly dropping, then they're going to be, each one that comes out is going to be a bit slower than the one before it, and in practice it just wasn't very fun. It made the things a pain to work with. So instead, capacitors work on a simpler thing. The voltage is whatever the voltage of the charge that it received was, and that's it. It just puts it out, and it puts it out at a specific, it just puts it out very specific mana flux. So a 2 charge, 1 charge, 4 charge, 20 charge, etc. It'll charge up till it has that much, and it'll release it. It's good for when you have low quality things like these garnets, where they have that 1 to 5 flux in them. If you have, say, a 4 charge, you're going to be putting out a pretty regular 4 mana. Also about the mana. When you're dealing with power, the normal formula for power is going to be, I squared R. This one, it's basically that, but there's a magical coefficient that comes before it. So it's I squared R, basically. So whatever ends up coming down here, you can see these are basically going to be multiplying your power by, 4 or 5, 3, 4, etc. So you can see here you got 1, 2, 3, 4, 5, 6, 7 of these conduits. Each one of them has a 0.1 ohm resistance, so you're going to have 0.7 ohms in the wires. Now this thing has a 10 ohm resistance because the runes themselves are a resistive element, and essentially their resistance tells how much power they're going to have available to use. So you're going to take the resistance in this and resistance in this. It's essentially, if you're familiar with partial power formulas, this one's just the partial power of that rune. It's going to be how much will go out. This one's just a light rune, so it doesn't really enter into it, but with the emitter runes it does, because the emitter runes will actually be emitting power out. One of the levels, the tutorial level, is actually a wand that has this gauge up here. This is the power gauge, and it needs to be between 20 and 50 watts. So, and it'll have 10. That varies. If you make it bigger, the resistance will go up in it, which will make it more efficient. If you have better quality tools, you can make better quality runes. Efficiency goes up even more. This one also has a 0.1 ohm resistance. So the overall resistance in this circuit will be 0.1 plus 0.7 plus 10. So that'll be 10.8 would be your overall resistance in this here. But this one's going to be getting most of the power. These ones will be dissipating power as a result of current flowing through them. I simplified that rather because how wires actually dissipate power is a complicated thing and not fun. So I just simplified it, and basically each one of these have a particular power dissipation rate, and they can dissipate at, let me pause and look at it. It's 5 watts. Basically each one of these, so they can dissipate 5 watts pretty much every cycle. That's 0.02 seconds. They have really good dissipation, but if you put too much through, they will burn out. Maybe I'd be able to demonstrate that. I don't know. Let's see. Good. Actually, let's delete that and these, and we'll put this one here. That there. I think that short might do it. No. That's not even enough to make it burn out. I'd probably need to up the power going through it. This one single thing just isn't enough to overload it. But I could. This is how you connect crystals in series. Oh, yeah, there it goes. Shop exploded in a giant fireball. Yeah. So, and that's the crystal that exploded because it's the one directly connected to it. Because essentially, when each one of these, they're 9 volts. So 9, 18, 27, 36, or something like that. 36 volts, and not a lot of resistance there. So that one blew, and then ultimately this one blew as well because of the short to ground. Not the best sprite for that. So here is an example of another puzzle. This one is the XOR gate. You can see it indicates, so you know what's what to expect. There's a truth table over here, and there is a tester that will pop up when you've actually set it up. Now this puzzle, you might think, how hard could an XOR gate be? Just look up a wiring diagram online and plop it in. Not so much. See, one of the big limiting factors here is your space. You only really have this much space to work in. And I spent, I think, a week trying to solve this puzzle. It was actually very difficult. Because basically what you have, you can get about 4 transistors in here. And let's see, you also need not counting the NOT gate. You gotta have a NOT gate or you're not gonna, it's the inverter rune here. Is your NOT gate. But essentially, now one other thing to note here is this. In a lot of them, the scale here is 1 to 1. One square is 1 inch. But here, the scale is 1 to 5. One scale is one square is 1/5 of an inch. And that is because when you've actually when you've solved the puzzle, you unlock the component. When you unlock the component, you can add it into other ones. So essentially, all of this will fit inside one square. That makes things a little bit easier. I'm going to go ahead and I will show you the solution. Maybe. So in the end, this is the solution. You can see here, I already tested it off screen, so you can see I passed all the tests. But when you press this tester shows up. And you can kind of see how this goes into the power, this one goes into A, this one goes into B. This is the set. This is basically, just for the heck of it, basic. So, when you're content, you press that and that'll actually do the test. So, let's see. If you press A here, you'll see this comes on. And so, A on, B off, light on, off, on. That matches. Similarly, when both of them are on, no light. That's what you'd expect from an XOR gate. When this one's on, light. And you can see that delay between them is why the set exists. I don't know if that's an issue with my game or just an issue with the solution itself. It just has too much resistance. I don't know. But yeah, you can see there's a delay that happens between that and that. And of course, none of them, nothing. And that's basically an XOR gate. The set is just basically for the user, for your sake. Let's see. These ones here, you'll actually see are earth crystals. When you see them flowing, well, you can't see them because they're going too fast. But these are actually channeling earth element through there. And that is because this should be fire coming out here, not earth. So it's so that you don't try solutions that are not accurate. You know, the power needs to be coming from here out to here. And be going from powered out, and these should be using for control. You shouldn't be using these should not be going straight to the output. So that's why they are a different element. But yeah, it's a tricky one. You can see here, these are OR gates. This is an OR gate. You have two transistors in parallel running there. This is an AND gate, having two transistors in series. And you can see that the output of this here goes here into this inverter room. So these basically, the outputs of those will both go into this. So if it comes out of here, it'll go there. Comes out of here, it'll go there. Or both in the case, because it is an OR gate. This is an inverter room. So what that means is that if power is coming out of here, if there is nothing coming in the base, just coming from this one here, this is the AND gate. This is the output of the AND gate. It's going into the base for the inverter room. So if there is nothing coming through, power will go straight through like it was basically like it was a wire. But if power comes out of this AND gate into here, then it turns off. It stops. The power from the OR gate will not go through. And that is what makes the XOR gate do what it does. So if we go back to here, what you'll see is A is on. So power is coming here from A into the base of this part of the OR gate. Nothing's coming from B. But if something was coming from B, now B goes into this one and this one. It also comes here, jumps over this line. That's a bridge right there. That's important. And into this one's base. This is going into the base for this AND gate. So in the AND gate, if this and this, then it goes into the base of this and stops this from flowing, as you can see by the color. But if only one of them, like B here, well, B is allowing it current to flow through here, through here, through here, and it goes into here, but because there's nothing coming through here, this does not turn off, so power is able to flow, and we get a nice little light. And our truth table will say, yes, everything is good. And that is how an XOR gate works. Now, this is, normally you don't wire up an XOR gate quite like this, because a CMOS XOR gate would not have them wired in quite this way. It's probably part of why there is that delay. It's timing issues related to the base and the collectors. So CMOS has an awful lot more transistors. I think actually I might have made one in the CMOS way. Let's see if I can find that. Yeah, here's an example of a video I recorded a while back with my phone. And this one is wired up, I think, more in line with the CMOS way of doing it. 2 inverters, and gate or gates. Yeah, but you can see it's also an awful lot bigger. And trying to fit it into this little bitty package, you gotta compromise a little bit. So yeah, if you're watching this video, then it means that you now actually know how to solve that puzzle. So, sorry if that was a spoiler. I'll try to stick to early level puzzles here out, but I really wanted to highlight that because I really like that puzzle. So speaking of early levels, this is the tutorial level. In this one, you have the Master Artificer. Basically, there's 3 phases to the game, and in phase 1 is the kind of getting you used to the gameplay, how to, it's basically your introduction, your tutorial. This one is the actual first level, the tutorial. And the Master Artificer here, who you are apprenticed under, will be directing you. I really like this design. So, yeah. This one covers, so that's a crystal, that's a conduit, that's an emitter room. Lets you know, this is showing you this is where the gauge is, this is what you need to be aiming for, and then he gets out of your way and lets you do your stuff. And essentially, yeah, the solution to this, this one isn't a hard puzzle, it's a tutorial puzzle. So it is actually really simple. He basically just told you how to do it. It does have 2 phases. The first phase is basically this. The second phase, which I haven't set up yet, he'll ask you to add a switch, because obviously a wand that is constantly shooting out fire isn't very useful. It's actually pretty dangerous. So that will cover this part, which is deleting conduits and then wiring in turn. It's not using up stock. I should do something about that. Looks like I have this set to infinite. I do that for debugging, but it should actually be subtracting stock if you use them. This says 100. Basically, you can make 100 conduits with it. Conduits are ones that if you delete them, you don't get the stock back, but you get crystals back if you delete them. Runes, they have numbers on them, but they don't matter because you never actually use up runes. But yeah, then this is just, if you do that, you'll see. Oh. Okay, so that's embarrassing. I made the game and I did that wrong. But it's okay. It's easy enough. So what had happened there, I'll show you what happened. It's working now, but when I added that switch right there, I connected this way. Don't connect that way, because that says that the flow is this way. What I should have done was this. That is how you correctly connect them. Then you'll get them flowing, and you can see the gauge doing its stuff. You can pause it, and it'll go back down. Pulse it. I like pulsing because I think it looks cool. But yeah, essentially, it needs to be successful. It needs to hold inside of this green area for, I think, like 5 seconds or something like that. And then it will go to the next stage, and so on and so forth. Okay, I don't know if you can. Hopefully the music actually comes through. I don't know if you can hear it. Last time I did a recording, it didn't go through. But yeah, this is just the opening area. The opening, you got the scrolling thing, background. So let's go ahead. Let's continue. And yeah, this would show up usually when you make a new game, not when you continue. But it's just set up right like this right now. This is kind of your introduction to the world. This is you, Alex Finnegan. And, it's got information. Pause if you want to read through it. We'll just skip past. This is actually a book that will be available in the game, which gives information about the world, about engineering. It explains a lot of the stuff, so it's kind of a reference book. I'll include a link to that in the description as well, if anybody wants to read it. It's not complete at the moment, but it has a number of chapters. And then that's just going to go back to the start, so we'll stop it. And putting the blinking lights back on, just because I like the blinking lights. So, anyhow, that is a lot of what's been done. There's a lot of other levels, but I'm not going to be showing them all off. I might show off the immovable rod in a future one, because it does cover some of the interesting things, but I don't know. I just wanted to make a video kind of highlighting what I've been working on here, and hopefully the goal is to have a demo available soonish on Steam. So and that'll be available for free, and the final game I'm aiming for somewhere in the area of $5 when it's completed. So look out for that, and I will leave it at that.